This is more or less what it looks like in Zio. This is a complete module, has everything we need in here to talk about and use console. And all the other modules look exactly like this. The module looks like this. It has that single field. And then there's the interface that gives us the bundle of capabilities or data. These don't have to return anything in particular. There's no requirements on these. This is just an interface. It's the interface. It's what you get from using the console module. This is a live implementation, and you might suspect that it's called live because there would be a reason to create a test module, and that's true. There would be a good reason. Actually, I need to extends. Here's what I'll do. Extends. I'll extend console here, and then what I'll do is I'll say val console equals new console.service. And I'll stick all that inside the console field. That way I won't have to do any construction work later. So this gives me something that extends console, which is the module. So this is a live module that inside it has the console service, which is an implementation of these two functions. And here I have my implementation of the two functions. So this works out very well. And now let me show you what we can do once we have a module like this. So once we have a module like this, we're going to want to access this module through the environment. So obviously one way we could access console facilities would be to create a value of this type, console, and pass it around to our programs. For example, we could say def console program, and we could pass around this module. And we could write our program over here. And inside here we could call console. We could be like, we could import that, and we could access put stir line and everything else inside this module. We could do it that way if we wanted. But Zio environment means we don't have to do that. Zio environment allows us to access any of our effects dependencies through the R type parameter, which means no boilerplate, no threading of any kind. All we have to do is declare this, the type of this, to be Zio console, and in this case I'll do IO exception and unit maybe. And now I can call Zio a function called accessM, and accessM gives you access to the R. Gives you access to that R environment. Yeah. So here I'm going to access my console, and then now I'm going to get my console here, and I'm going to import all the goodies inside that console in here, and then I'm going to write a for comprehension that does something. Oops. And then I'll yield the name down here, change this into a string. So there you have it. Using the module pattern, you can access it through accessM. You can access the environment. In this case, I only need console, but if I wanted more things, I could access console with system, with clock, and so forth. I can just add whatever I want to access, I can just add it here. And then I'm going to get the modules in there, and then I can import it as I see fit.
So the question, so if the type of console program is Zio console system clock, say, can I still do the Zio access and console?
Yes, due to contravariance, you can still do that. So it's okay to only access a part of something that's very big. You don't need to access everything in your environment. If you just need one thing, you can access that. And that will be considered to be a subtype of the thing that has everything. So due to the way contravariance works in Scala, that works out fine. Question?
Where's CMD actually coming from? Is that like an argument passed on, say, run?
You don't actually have to drop down to that level. So let's talk about that. So I have my console program here. In fact, at this point, I'm just going to delete all this because I don't need it. I showed you what that looked like, and you can look in Zio if you want to see that more. At this point, I have my console program, but this requires a console. I need to eliminate this console if I want to unsafe run it. Actually, you don't need to do this because the default unsafe run in Zio bakes in all the standard things, so you don't actually need to do this, but let's pretend you did. If this were your own module, you would have to eliminate this. This effect requires a console. We need to give it a console to turn that into any. Once we turn it into any, then it doesn't need anything, so we can go ahead and run it. So how do we do that? Well, we call console program, and, oops. Let me compile this, make sure it compiles. All right, so we got it compiling. So I call console program and I call provide. And now what I do is I call console live on it. I give it the console live. So now this is like running the reader mode ad. It eliminates the R. Actually, it doesn't eliminate it per se. It turns the R into an any. It turns an effect that requires an R into an effect that doesn't require anything. And once I have an effect that doesn't require anything, I can call unsafe run on it, if I want to. Maybe after I provide this console, I'm going to compose this together with other effects and so forth. You can do local elimination. You don't have to eliminate this one time in your program. Question? Yeah, provide is, the question was, is provide acting as the runner of the reader monad? And yes, the answer is yes. So the signature of provide is as follows. Given a Zio effect, and an R, it's going to eliminate that. I'll just use IO. Or no, I'll just so you can see what it is. So you give it a Zio effect that requires an R, and you give it an R, and it's able to take that R and feed it into the effect and eliminate its requirements. And you end up with an effect that doesn't require anything. That's how you do elimination of dependencies with Zio. Question?
You have to supply the whole R, you can't provide.
You can provide some, yes. There is a provide some that you can use if you only want to provide some of it now, which is very, very powerful.
So does the implementation, once they run, also do a provide of all those other modules?
Yeah, that's right. Yeah, so if you're using the stuff baked into Zio, you don't actually need to provide anything. But when you start building your own modules to represent different services in your system or configuration information or whatever, then you're going to have to call provide to eliminate those, or provide some if you just want to provide a piece of that R. You want to provide a piece of the R and leave the rest of the R for someone else to take care of. Another question? No? Oh, same question. Okay. Yeah, so provide some. That is a very common question, and yes, you can do provide some when you want to eliminate a piece of that R.
Can you talk about how that might differ from dependency injection?
Right, so there's two, the question was, how does this differ from dependency injection? Well, the first off is this is nice and type safe, purely functional, also composable and modular, so you can eliminate dependencies anywhere or reintroduce them. So nothing is special or privileged. In dependency injection, your modules are special and privileged, and you inject them by the constructor or Java Bean style getters and setters. And deep down in your code, you don't have the ability to inject dependencies. Whereas nothing is special here. It's all ordinary functions and values, all pure FP. And you can be very modular because at any point in your program, you can introduce and eliminate dependencies. So you have introduction and elimination of dependencies up and down your whole stack, and that's the essence of modularity. It's type safe, so there's no possibility that this fails. If it compiles, it's golden. Whereas with dependency injection, depending on which framework you're using, that's not necessarily the case. Now, dependency injection is actually bigger than this. You could use dependency injection with Zio environment. And the reason for that is dependency injection solves two problems. First off, it solves the problem of threading stuff through your program. It often solves that problem. It often will automatically find all these classes and thread these things through and create them and pass them and so forth, so you don't have to solve that problem. But beyond threading, it solves the wiring problem. It provides you tools to wire up this package of things in a production environment and in a test environment that are different. And Zio environment does not give you any tools to construct these Rs. So there's zero help for wiring. When you want to wire up an R environment, you're going to be building up these things yourself using, classes and constructors and with and so forth. You're going to be saying new this, and so forth. You're going to be wiring that stuff up manually, unless you can find a way to use an existing dependency injection framework to do that for you. I think actually MacWire might work with Zio. If you're familiar with that, MacWire would probably work with Zio. All right, so this is not exactly the pattern that you're going to find in Zio, but it's close. What Zio does is, instead of requiring you access your modules through accessM, it actually defines a bunch of helper functions, which just call the accessM for you. So in actual Zio code, this would be even simpler. It would look like this. Where all these functions are coming from console. In fact, I can import them here. So they're all coming from from here. So I import them, and then now I'm using them as ordinary functions. So no more accessM, that's gone. That's not even the best part, though. The best part is, unlike tagless final. What's that?
Can you explain how this works? How does it do that?
If you look inside console, you're going to find a definition of putster line like this. This is a helper method, and these helper methods are baked into Zio just to make it easier so you don't have to do the whole accessM thing. So the really nice thing about this is, unlike tagless final and premonads and everything else out there, this fully infers. That means you can delete all these type signatures or have the IDE construct them for you. And it works 100% of the time. And not only that, but you can combine effects in a for comprehension, and Scala will infer the correct type up here. So if I'm using the clock in the database, then I just have to call my functions in here. I don't have to specify anything. Scala will infer this to be clock with database as my R.
Replace get string with clock.
What's that?
Replace get string with clock so we can see that.
Oh, right. So let's do that one. Let's do time. Let's do clock dot current time. Let's say days. No, what's in here? Yeah, days. And my name is gone. I'll just yield the time. So I can't hover over this. This doesn't have type. Oh, it does. Okay, there. This is new metals feature. This is awesome. So clock with console. So I can use all these different things inside for comprehension, and I never have to worry about the effects. They're all inferred flawlessly. And then if I have like a coding convention to put top level type signatures, of course I can do that, but I can use the IDE or Scala compiler to help me. And if you get the type wrong, then the Scala compiler will prompt you to keep on adding stuff until you get it right. So you have very good compiler assistance for this, which makes this a very pleasant thing to use on a day-to-day basis. Question?
Will I miss writing all the boilerplate?
No. If you're stuck in the world of tagless final, you will never go back. after using this, or free monads, tagless final, just so much boilerplate. You're never going to go back to that. It's just like, I know the benefits of tagless final. I like, polymorphism in my code, but I don't want to write that code. Sorry, I'm out. It just provides too little benefit, in my opinion, for the very tiny amount of improvement to reasoning that it provides.
Sorry, a real question. Do you use tagless final and free a bunch of macro stuff in order to make writing easier? You can enable that stuff. Is any macro stuff required for Zio, or is it all straight Scala?
The question is any macro, obviously tagless final and free, they have lots of macro stuff, like generating lots of code to make those things somewhat usable. And you still have lots of boilerplate, and you still have type inference problems. Like, you have all these problems. You can't omit types in tagless final. You can't do that. So there's a lot of boilerplate problems in tagless final and free programs, despite all the macros and code generation out there that's been done to make that easier. And the question is, well, do you need any of those macros or code generation for Zio environment? And the answer is no, you don't need it. There's actually 0 macros, 0 code gen in the Zio core library. And you can see how straightforward it is. These are just interfaces, It's a module that contains an interface, basically. That's it. And this is ordinary Scala code. There's nothing new to learn. There's no higher kind of types. There's no compiler. You don't have to trick out your compiler with, the special case of trying to infer the F, which you can do in some cases, but not others. You just use the ordinary Scala compiler. It works on 2.11, 2.12, 2.13, and even Scala 3, this technique works on.
When you're writing a lot of Zio, do you typically write these helper functions that do the access M? Or is it considered a bad practice to do the access M like within your business logic?
I think you can go either way. My preference is I don't like nesting in my program, so my preference is for writing the helpers. But actually, I think people who are not me prefer access M, because then you don't even have to write the helpers. And if you have one function that is like, 20 lines of code, you're accessing 2 or 3 things there. It's one access M in that entire scope. So that gets it down to a reasonable level where you don't even really need the helpers at that point.
So if you do something like an IOEA, flatmap, ZIO, R1 EA, flatmap, ZIO, R2 EA,
Yeah.
you end up with a ZIO, R1 with R2 EA.
Yeah, that's exactly right. The question was, if you have an IO EA and you flat map it with a Zio R1 and flat map that with a Zio R2, what do you end up with? You end up with a Zio, technically any, with R1 with R2, which is simplified to R1 with R2, because of course R1 and R2 have a supertype of any. So as you're flat mapping, this is the way type inference in Zio works. As you're flat mapping, errors are being unified into the common supertype. So if this one can error with an IO exception and this one can error with a number out of bounds exception, then when you flat map over those, you end up unifying those to exception, which is the common parent of those two. And the way dependencies work are you're flat mapping over these things that have different requirements, then all of those things are combined together using intersection, and you have this requirement with that requirement with that requirement with that requirement. You end up with this thing that contains the dependencies for everything. Another question.
Could you show this, like, where you use the provides to give it so you can run it?
Right, so let me do that here. So the question was, where do you use the provide? So here I'm going to do this.provide console.live. Now I've eliminated the effect, and now when I save this, oops, sorry, now I need a new console live with, what am I using? Clock.live. Java time clock. It's going after the wrong console.clock. Fully qualified? Oh, well, right, okay, I see. Yeah, you're right. It's clock.clock, right. So maybe this less qualified one will work. Okay, there we go. So this thing required two things. It required the clock, and it also required the console. So I need to give it an R that has both those two things in it. So this is what I mean when I say that dependency injection, you know, it helps you do the wiring. Here I'm doing the wiring myself. I'm wiring up this R to contain all the things that I need. Now, is this a big enough pain to carrot you towards DI or not? I don't know. That's up to you to decide. It depends on how big your application is, how many different scenarios you have, and you know what dependency injection framework you might be considering for use with Zio. Personally, for reasonably small programs, I would not introduce a DI framework just for that.
But even if you compile or something, you need to stick those models together. So you look at the reason one of this.
Right. So the type of this console program is IO nothing long. So we can look at it and we can know that, number one, it doesn't require anything anymore. Why? Because we gave it everything it required. We eliminated that. And also, we know that it can't fail. So we know the functions we're calling in here can't fail. Puts through line, current time, can't fail. And then finally, we know it returns a long. So we're looking at that type, and we have an enormous amount of information, which is 100% inferred by Scala, so we didn't have to write that. And that's not a big deal for those of you coming from Haskell, where everything infers. But for those of us in Scala, we've lived with terrible type inference for so long, at least in the FP subset of Scala, and finally we're getting things that infer very well by changing the way we're approaching functional programming in Scala. All right, so let's do a few exercises just to get a feel for this. All right, so in this one, I want you to write a little program. You can make any program you want, but here are the requirements. You need to call at least one method in clock, at least one method in console, and at least one method in random. So you're going to use clock, you're going to use random, you're going to use console. And then after you write that little program, figure out this type. And obviously you can cheat here. You can use your compiler to tell you what the type is. But see if you can write a little program. Maybe the program should print out the current time, and maybe it should pick a random number, and maybe it should ask the user to guess the random number. So see if you can write this. If you can write this, then you're in really good shape. We have an hour left of this workshop, and if you can write this program here, you're in really great shape for using Zio, I think. A previous question I missed was, what does adding tasks to manage do? It keeps us from actually opening the file until used. Yes, it's keeping our code, everything suspended in this pure data structure so we can reuse these things and write combinators on them and so forth. It's keeping us in the world of pure FP. And it's required by the types, which is why I got type errors. I wasn't doing the right thing. I forgot to wrap those things in task. I did, right, I had to do clock dot, or no, was it clock? Yeah, it was clock dot whatever. I'm not sure what's imported in here. I think it might be missing some imports. We've got console, but it does not have clock. And random.
If you are using the access end, can you use width in the type parameter of the access end?
You can. Yeah, that's no problem at all. Oh, so let's see, what can you do here? Well, you could say, All right, this is my simple program. I get the current time. I print out the current time is whatever in number of days. Or I should say, I guess the current hour is that hour. And then I say, please guess a number between 0 and 10. I choose a random number between 0 and 10. I get a line of input from the console, and then I just check it to see if whatever they entered. Oops. I'm going to trim whatever they entered is equal to the string representation of the number. And if it is, I'll say congratulations, you guessed right. Otherwise, you guessed wrong. And the inferred type of this program is clock with random with console. And the error is, what was it? IO exception, and the return value is unit. But no, maybe not. Yes, I think it is. Very nice. So one of the questions was from James, how do we compose the live objects to provide the environment? And the answer is use with. Use with on the traits to with them together. You knew this with that. And I did show one example of that. I can show another one later if people want. All right, so looking at the type of this program, what can you tell me about what it requires? Requires three things, doesn't it? Clock with random with console. And how about, can it fail? Yeah, it could fail with an IO exception. Where's that coming from? You can look with your IDE and figure out where it's coming from, but can you see it? Yeah, it's coming from getStir line. Because there's some possibility that you try to read some input from standard input, but standard input has been closed. So it's possible that will fail with an IO exception. And then finally, this returns unit. So the type signature here tells you quite a lot about what this thing does. And obviously we can run this program just by calling unsafe run on it, or by providing it the live stuff and then running that. But one of the interesting things about this program is it actually has no external dependencies. None whatsoever. We can run this with a test clock, test random, and test console. So when we run this, we can run it, we can pretend it's whatever time we want it to be. We can generate whatever so-called random number we want. We can collect all this console output into a list of strings, and we can feed it in some line as input from the console. And this program here doesn't change at all. It's the same program. Question?
While trying to work on this, I ran into no obviously named filter methods on Zio. Is there a way to conditionally filter out a value into a potential failure? Or do I have to flat map?
You want to conditionally fail?
Yeah, so take a success value, apply a predicate to it, and then if that predicate doesn't pass, then fail.
Fail with what error?
Would provide error.
Yeah. You want to do a predicate on a value. So it's not quite what you want, but there's when. Did you see that?
Yeah. I was looking for something like either's fail or maybe it's filter or is the on either.
Yeah, we should add that. That would be handy. Good first pull request. Yeah, right. Okay, so we can take this program here, and even though it looks like it's sort of fully specified, we can run it on test clock, test random, test console, all of which are baked into Zio, by the way. So you can run this, and you can write deterministic unit test that runs instantaneously and doesn't interact with the real world. And that's part of the power of using Zio environment. Because it's so painless, relatively painless to pass dependencies through your program and have them totally infer, there's no reason not to do it, especially in code you want to test. Now you don't have to start out that way. You can start out just using task if you want. But the point is, Zio has a migration story. When you can start out simple, just using it as a better future. But over time, you can upgrade it and say, okay, we're going to introduce an error type here because we need a domain error. Or maybe we want to eliminate errors. We want to use UIO to make sure we've handled exceptions in this critical part of the code. So you start upgrading and you start taking advantage of type errors. And after type errors, eventually you run into a situation where you're like, this gnarly bit of code, it's interacting with the database. It's sure hard to test it with a real database. It would be nice if we could supply a test database without having to do bytecode rewriting or anything like that. And then you just change the type signature of that function to require a database in the environment, and you don't have to thread it. You don't have to thread that. Zio will take care of that because of its built-in reader effect. And then you can incrementally refactor your code, making it better and more testable over time. You can start with something simple. You can upgrade over time to use all the features of Zio. Question?
If you add with system to that type signature, will it not compile?
It will compile. So if I add with system here, it will still compile. Why? It will compile because it's okay for a function to be provided with more than it needs. Zio's R type parameter is contravariant. You can give it something bigger than it actually needs. And conversely, how to state that is Scala, the Scala compiler, can always infer a subtype as if it were a supertype. It can always see a cat as being a type of animal. So you can always give a cat a type of animal.
You can't look at it and say everything in that signature is being used in the function body.
Well, right. If you want to do that, then I would say, delete it, and then have IDEA insert the signature for you, or just leave it deleted. Honestly, I personally don't think that you need type signatures in code like this. You don't absolutely need them. If you have a good IDE, if you have a good IDE that can tell you what it is, then you don't need one. And that way you can't get it wrong. Clock with random with console. All right. So did everyone get that program example? Or something similar?
Again, through a series of flat maps, those modules are still available all the way through that entire chain, right?
Well, you can add things that require them all the way through the chain. What happens internally, though, is the first flat map starts out with one R, and then it starts gradually broadening it. Every additional flat map adds some more information to that R until you get to the bottom. But if you add something that requires something else at the beginning, then you start with that bigger set, and so it all works out. But that's the way it is, gradual widening.
You have everything required up to that point.
Exactly. Yeah, if you look at the type, if you just copy paste that section of the for comprehension, you'll see Scala will infer that to be everything you've used up to that point. Any other questions? Yeah.
Do you have an example of like an environment module that needs another environment, but I, as the user of that environment, don't want to care about that other things dependency?
Yeah. Yeah, so for example, clock is like that, because clock actually has a secret hidden dependency on scheduler. The clock module in Zio uses a scheduler for the sleep functionality. So if you want to see a real life example of that, because you sometimes want to hide your dependencies. You don't always want the whole world to know everything that you require in order to provide some service. So you can do that using Zio. There's two different techniques to doing that, and one of them is just to, inside your implementation for a module, you extend whatever else you require. So you extend it. And then no one else will ever see that implementation except whoever wires up this big long, production thing, production R. And anyone who interacts with the service will not even know that your one service depended on another service. They won't know that. So that's a very simple way of doing hiding that was used in the days of the cake pattern. So it's very familiar to people. So I recommend people start with that one. And then if you want to get fancy, then there's a way to get fancy. All right, so in this exercise, you're supposed to build your own config module. So config is a major reason to use environment. In fact, maybe that's the way you start in your application. Lots of different parts of your application require config. And a nice thing with Zio environment is that you can have different parts of your application require just the little bits of config they need. And then you can whiff them all together. They'll be inferred to be the super type. So you can end up, you have to provide all the config, eventually at the top, but different parts of the application don't need to know about the types of config that only they need. And basically you don't have to do sibling sharing. You have to do parent to child sibling. If you call a bunch of things that require more config, then you're going to know about that. But the sibling to sibling sharing, you don't need to. That's not going to affect the type signatures. So you can get away with hiding that information from siblings. So config, in this case, actually you don't even need to use ZYO here. You could just have int and string. Remember, there's no requirements on what these services can have. It's going to be common for them to be effects. That's why this approach is called environmental effects, because it's very common, but they don't have to be effects. They could be ordinary data. And in the case of a config, in fact, maybe it's just a bunch of data. And you use that to get config to the distant remote parts of your application without having to thread it through parameter lists and do all that plumbing yourself. So we won't cover that here because we've got other stuff. We've only got roughly half an hour. So you can do these exercises on your own time and figure out how all this stuff works. You can build a runtime. The default runtime bundles the default environment, that is the environment that contains clock and system and console and all that stuff, together with a platform, which is the low-level thing that Zio needs to execute an effect. You can build your own. Quite simply, a runtime is just a bundle of all this stuff together with some platform. And you can use the platform that already exists, and you can supply your own runtime, so you can create a runner that can run a runtime that's very specific for the global type of environment required by your big application. And then you can use that to unsafe run anything that has that type. And you don't need to do that, by the way, because you can always provide. You can provide to eliminate the R, and then you can unsafe run it using the default runtime. But I do think this approach is nice for some, especially for integration with Cat's effect libraries. Here, this asks you to do the same thing for a file system, so good exercise to do if you want to know more about building these things. We're going to actually, we'll take like a 5-minute break because I want to dive into concurrency. I want to show you some of the ways that Zio makes it very easy to do concurrency. So we'll take a 5-minute break and then we'll wrap up with a brief tour of concurrency in Zio. So let's briefly talk, before we dive into some of the concurrency and parallelism combinators, let's briefly talk about fibres. So Zio uses a fiber-based concurrency model. Fibres are like threads, only they don't actually have the overhead of a thread. So Zio's fibres, they don't block. When they stop executing, they stop consuming resources. So they share threads. You can use a small number of threads, actually just one, to run a huge number of fibres. And that's a lot more efficient than creating one heavy-duty operating system level thread for every single thing that's being done in your system. Also, there are some other advantages to using fibres over threads. Not only is it faster and consuming less resources, but also it's more flexible. So fibres, they have a shrinkable, growable stack size, whereas your JVM threads have a certain amount of fixed allocated stack space, and when you exceed that, of course, you get stack overflow exception. Zio fibers, as they're executing, they will consume as much heap as they need to when they're building their own stack. They have their own stack. It's not part of the JVM stack. It's actually stored on the heap. And as a result, it can keep on growing and growing and growing up to the limit of the computer's memory. So you can actually consume 100% of the computer's memory in the form of this reified stack that is used by a fiber. That gives you flexibility. So like I said before earlier today, just because you have a function that's not tail recursive doesn't mean it's going to blow the stack. It's not going to blow the stack. It'll just consume heap, and if it eventually terminates, that's fine. So it means less worrying about the sort of minutia of how things are executing on your machine and more time solving the problems that you have in the business. Also, interestingly, fibers can be garbage collected. So you can, for example, have a queue and have a fiber that is reading from that queue continuously in a loop forever. Now, if someone stops putting things into the queue, and if no one is referencing the queue anymore, then both the queue and the fiber can be garbage collected, despite the fact that the fiber was going to be running forever. If a fiber is suspended, which is what happens when it has no active work, and if it cannot be reached anymore, if basically its means of being reactivated cannot be reached, whether it's a queue or whatever, then that fiber can be garbage collected and will be garbage collected by Java. That's not true of threads. Every thread resource, if you have a thread that's waiting for something from a blocking queue, it doesn't matter if no one's ever going to put anything into that queue again. The thread will keep on blocking forever on that, and so you need to pay very close attention and make sure you shut down that thread. Not only that, but the thread's access to the queue will mean that that queue is considered a live reference. And so the queue, neither the queue nor the garbage nor the thread that is pulling from the queue will be garbage collected, even if there's no possibility that anything will ever be placed into the queue again. So threads make it very, very tricky to manage resources. Fibers make it a lot easier because in many cases they'll just be garbage collected automatically. They have shrinkable and growable stack sizes and so forth. And of course they're way more efficient than threads because you can have, roughly I'd say there's a limitation of around 10,000 threads on a modern computer. You can have around 10,000 threads before you start getting into the point where threads just consume so much overhead, context switching between them, and so many raw resources that it just doesn't become tenable to go up beyond that. And the limit for fibers is much higher. Conservatively, you could say you could have 100,000 fibers executing on a single machine, and that's conservative. You may actually be able to get away with 1 million or more than 1 million fibers executing concurrently on a machine. And that's because, again, fibers consume no resources when they're not active. So they're super lightweight. And they have that growable and shrinkable stack size, so if they're not doing much work, they're not consuming many resources. Question?
Fiber gets garbage collected. Anything that was inside the fiber using a resource, they'll all get shut down.
Right. So the way that works is basically, let me think this through. So yeah. So the fiber's activity. I have to think more if there's ever a situation that could result. The question was about garbage collection. What happens if a fiber that is suspended indefinitely is garbage collected? And I have to think. I actually have to think about that question and figure it out. I actually don't know, so I'll get back to you on that. All right, so ordinarily, you don't have to deal with fibers directly. A fiber is actually a low-level thing. It's like a thread. But occasionally, and also just to know how Zio itself works, it's useful to be able to talk about where you get fibers from. And the answer is, you get them by forking effects. Actually, you can get it in other ways, but the main way is by forking effects. So if you have an effect here and you call fork on it, then you're going to get back that fiber inside an effect, of course. Because when you call fork, you're not actually starting it right now, you're just describing the act of starting it later when unsafe run is called. So with this fiber, there's several things you can do with it. You can interrupt it, so you can cancel that fiber if you decide you don't need its result. You can join it, which awaits for its result to be made available. Or you can await it, which just peeks on it. Doesn't join it, just peeks on it from afar and sees what happens with the life of that fiber. Let me show you an example of me putting hello Zio to the console. You can call forever on any effect to get back an effect that does that effect forever. And then forking this into a separate one. So this creates a fiber that runs forever, infinitely printing hello Zio to the console. You can also create fibers from raw values. So you can actually create them, if you have a failure or a success, you can create a fiber from that. It's like a fake fiber. It's like a fiber that's already done with its work, and there's its value. You can join fibers, you can await their results, which gives you this thing called an exit value. An exit value is a comprehensive description of how a fiber ended life. You're going to get the full cause in there if there's a failure, and then you'll get the success if there's a success. Poll is to check on a fiber to see, oh, are you done yet? Yes or no? So you can check on that. Check on the execution of a fiber with poll. Interrupt is to halt interruption of the fiber. And this will work if the fiber is in an uninterruptible section, is inside an interruptible section. So if it can be interrupted right now, it will be interrupted right now. Interrupt will not return until the fiber has been interrupted. So that means if the fiber is in an uninterruptible section, then it's going to basically wait until it gets outside there, and then it will interrupt it, and then interrupt will return. And if you ever don't want to wait around on anything in Zio, you can just fork that off into its own fiber. So if you call interrupt on a fiber and you're waiting for it to terminate, and you decide, oh, I don't want to wait for it to terminate, then you call interrupt.fork, and now a new fiber gets to wait on that, and you can ignore that fiber. So that's how you do fire and forget in Zio. If you don't want to wait around on something, just fork it and ignore the return value.
Can you explain what you mean by wait around? Like, isn't it like in Zio
Right. So when I say blocking here, I only mean semantically blocking. So for example, if you call io.sleep for 100 milliseconds, it feels like it's blocking. And you're going to flat map over that, and it will continue after 100 milliseconds, but it's not actually blocking. In the same way, if you join a fiber, it's going to block until the fiber is done. It's not actually going to block. It suspends the fiber until that result is available, and then it resumes when it's available. So you're absolutely correct. The question, by the way, was, does Zio block? The answer is no, Zio doesn't block, and anything that seems like it's blocking, like join or interrupt or whatever, doesn't actually block. When you call interrupt on a fiber, it suspends the fiber that's calling that until the interrupt succeeds, and then that fiber resumes. So it's not actually blocking the thread, it's not consuming resources, it just enters that state of suspension. All right, so those are what fibers are, and those are the operations available to them, but I'm going to skip over them because, like I said before, they're fairly low level. Fibers are things that you build concurrency and parallelism primitives from. Hopefully you never have to use them. You'll probably occasionally see them, and you should at least know what they are, but hopefully you won't have to mess with them much because there's much higher level means of doing concurrency. Fiber ref here, I'm not going to cover this because I'd rather not spend time on this, but this is a very powerful structure. Has anyone used a thread local in Java? Unfortunately. Right. So thread locals are very useful when doing multi-threaded programming because every thread can have its own copy of the information. Those copies are totally independent. They're useful in logging. quite a bit in logging, because that way this thread can store some information here in the logger, and ultimately it will be accessed down here. And it's how you do tracing and lots of other things in applications. But first off, thread locals are not very good for modern day programming. If you have a highly multi-threaded system, then thread locals, the use of thread locals starts breaking down and not being as relevant. Because one thread spawns another, well, that new thread that it spawns doesn't get the same value for that thread local. It has to start from scratch. And so that leads to all kinds of complexity. Thread local it was a good idea initially in the old days where threads were long-lived. Threads were long-lived, and mostly they didn't create other threads. It's a bad model for today's programming. And also, thread locals are not useful for fibers because fibers are not threads. Remember, one thread could be executing arbitrarily many fibers. So a thread local is not useful anymore. It's a dead concept. It can't be used with fiber-based concurrency models. So instead, Zio has something called a fiber ref. And a fiber ref is basically like a thread local, but at the level of a fiber. But it's an improved version of a thread local. So if one fiber is carrying along its ref and it forks another one, then that fork gets the value of that fiber ref at the time that it was forked. And conversely, if that fiber goes along for a while and it forks another thing, it gets the value of the fiber ref from its parent and so forth. So fiber refs follow the forking graph. So as things fork off from one another, they all inherit their values. And not only that, but if you call join, so if you join a fiber, then you get its fiber locals. So fiber refs follow the fork join graph. In other words, they can be used to propagate information even in highly concurrent parallel applications, propagate along the line of execution. And that's very, very powerful because what it allows you to do is, for example, on a web request, if you're building a web API or some sort of REST API, you could tag things by the request ID and the user. And then as that ends up being propagated into lots of things that are done in parallel and databases and caches and this and that, executing over tons of fibers across your entire system, they all have access to that fiber ref. And that information can appear in logging, in responses, and whatever they're doing, auditing, metrics generation, all that stuff can be propagated throughout your application along the lines of fork join. So they're a very handy feature for providing insight into the guts of how an application is working. That's the main use of fiber ref. Of course, you can use them for anything that you would use a thread local for, but in most cases you wouldn't use it for anything other than surfacing information, propagating information along the fork join graph. All right, so now let's talk about parallelism. Parallelism is very easy in Zio. All you have to do is call the parallel combinators. For every sequential combinator like zip, there is a corresponding one that works in parallel, and it's named the same thing, only it has the par suffix. So if you want to do something in parallel in Zio, just add the words par to whatever you're trying to do. And then suddenly it's going to be done in parallel. So zip par zips two things in parallel. CollectAll par is a nice one to use. You can use it to do for example, we have this get user function. And we have all these users. So what we can do is we can do something like, oh no, we have this list of IDs. So we have a list of IDs and we call map on here and we get user for that ID. And then we end up with a list of effects, and then we call CollectAll in parallel to turn that list of effects into an effect of a list. And this works in parallel. So it's basically all the effects in that list are being executed and those results collected back into a list. Yes?
So you would control the
Yes. Yes. So sometimes this could be overkill. If you have 100,000 things in your list, it's probably not a good idea to spin up 100,000 fibers. So, actually, I'm surprised we don't have this one.
You got an extra O on the Z.
Oh, maybe that's why. There we go. That's more like it. So you just specify the number here. And now the parallelism is limited to 5. So it'll be done in batches of 5. So all the parallel combinators that work on collections of things, at least I hope, they all have the N version. And the N version lets you specify the parallelism number. Now this is a very common pattern here. This is so common here to map over something and do an effect for each one and then collect it all, that there's a name for this operation. It's called ForEach. And ForEach, you just iterate over these things, and it's an effectful for loop. And then you specify what you want to do with each one, and then you end up with those results collected back in a list. This is traverse. If you're already a functional programmer, you know this is traverse. So you're just iterating over this thing and calling this for every one of these things. And the nice thing here is that we have the par variant. So if we want to do all this in parallel, it's literally 3 letters to change that. And then of course, if we want to limit it to say at most 5 fibers executing at one time, then we add the N variant. And now we're doing all this stuff in parallel up to a limit of 5 things at a time. Here's an example of for each par. I got ahead of myself. For each par is quite nice. I really like it. Zip par down here. Racing is the first sort of concurrent primitive that we run across. Race will race 2 things in parallel. And whichever one succeeds first, that's the one that will be the return value of the composed effect. This is very similar to future's first completed of. Only the ZO primitives are way more efficient than future. For example, if you try to do 10 things in parallel with ZO, and one of them fails right away, then the other 9 will be canceled right away, and they'll clean up their resources and they're gone. If you try to do 10 things in parallel with future, then what will happen is, I can't remember the method that does this. Actually, it could be considered collect, I think, or sequence. If you do this with future, then what happens is the first one fails and all the other ones continue to completion, but the overall future you get back from that has failed. So you end up wasting a huge amount of work. All the future primitives that should cancel computation don't, because future cannot be canceled. And it's the same way for race. If you do future first completed of to get back the first one, all the other ones will keep on executing till they're totally done. It doesn't matter that you won't use them. Those things keep on executing. Wasting resource, wasting socket, wasting memory, wasting network bandwidth, all that stuff keeps happening in the background. ZO, on the other hand, you race a bunch of things, and when you get the winner, you don't need the other ones anymore. So all those can be safely interrupted. A race attempt gives you, basically, you're getting back the first one to finish, not necessarily the first one to succeed. Sometimes you use this variant. And if you have a whole list of things that you want to race, you can use race all. All right, ZO has a reference here. This is the thing I was talking about. That's the purely functional version of var. So if we want to use var, ref is probably a better bet. And ref is a better bet because not only can you make these things and you can get and set them, but even more interestingly, it has atomic operations like update, which can be used to atomically update something. So refs are concurrent safe. They can be used by lots of fibers. If you use them instead of vars, then you never have to worry about stale caches. You never have to worry about race conditions or collisions as long as you're using the update or modify methods on this ref. And it is quite fast. These refs are very fast. A promise is the same thing that it is in the Scala standard library. It's basically a way it's a variable that can be set once, and other fibers can wait on that variable from being set. How many people have used futures promise? So you often use a future promise when you want to return a future, but internally you want to hold on to something that allows you to set that promise, which will then resume the future. And Zio's promise is the exact same thing, except instead of returning futures, you're returning effects. So you're going to create a promise, and then you can return an effect, and then you have a handle that can be used to resume that effect later when you have the result that you want to complete it with. We won't look at that, but you'll know when you need this, basically. You'll know when you need a promise. Zio has a queue as well. This is a very fast queue, and this queue is written using a zero allocation ring buffer. That's a part of Zio. It is asynchronous, so this queue never blocks. Neither offers nor takes from the queue ever block. However, it is semantically blocking. So even though it doesn't block threads, if you call offer and the queue's too big, then you are suspended until there's room in the queue. If you call take, but the queue's empty, then that fiber is suspended until something is put in. This gives you two-sided back pressure. It's a queue, a high-performance queue with two-sided back pressure that doesn't block any threads. And what two-sided back pressure gives you is you can make sure that the producers slow down. After they fill up the queue, it's got to capacity, then you force them to slow down. And also the takers, once they get ahead, they've caught up, and they take, then the queue's empty, well, then they're forced to slow down until more stuff is added to the queue. So if you build a data processing system or whatever type of processing you're doing, event processing system using this type of queue, you never have to worry about producers being too fast or consumers being too slow or consumers being too fast or whatever. Everything will just work. Question?
Is this an equivalent concept to reactive streaming, or is that a higher level construct?
That's a higher level construct. A queue can be thought of as a push-based stream. It has some similarities to a push-based stream. Question?
When you have this kind of processing queues, one of the challenges when you terminate the system, you want to wait for the push times before you can shut down the queue. So is there any construct that you do?
So there's nothing like that yet, but that would be a good addition, a wait for the queue to be empty. That would be a good addition. Yeah, that would be a good addition. There is a way to wait until the queue's shut down. So you can do that, but you can't wait until it's empty, currently. So that's queues. They're very handy. It's very easy to build nice things out of them. Semaphores, does anyone know what a semaphore is? Okay, good. Use semaphore to ration access to a certain finite number of resources. You could use them to bound request pools or other things. The semaphore in Zio doesn't block threads, unlike the semaphore in Java, for example, which will block threads. This one is an async semaphore. And the semaphore and queue and all the other data structures in Zio, they work well with interruption. And they work beautifully with interruption. If you interrupt something, if you interrupt the take of a queue, for example, it'll clean up all its resources and stop taking. It may seem like a simple thing, it's what you want to work, but actually turns out it's not so simple to implement that. Zio's own data structures go to the care and concern to make sure everything plays well with interruption. And then the last one we're going to look at before we're out of time is Zio Stream. So Zio Stream allows you to do effectful streaming in a way that doesn't leak resources. So you can stream over sockets and files and persistent queues like Kafka and so forth. And you have the very strong guarantee these streams never ever leak resources and you don't have to manage those resources yourself. And you can stream over infinite sources of data in a finite amount of memory. You can do heavy duty data processing in fixed amounts of memory with these streams. They're very easy to use. They have an API that's very much similar to List or whatever. So you can construct these things directly. You can build them from iterables. You can build them from chunks. You can build them from lots of things. You can build them from queues. Structures in Zio have good interop with each other. singleton strings, streams from effects. You can unfold a value into a potentially infinite stream. You can add effects to the elements of the streams, filter them. They have a very collection-like API, so you can filter, take, drop while, take while, ForEach, and so forth. You can do all these different things with streams. And you can run them. To run a stream requires a sync. A sync is a stream can be thought of as a source of elements, and a sync is, well, a sync for elements. It accepts elements and builds something. And syncs compose together to yield other syncs. They're kind of like parsers in that way. So you don't have to use a sync if you don't want to, but eventually if you're parsing complex things or changing from JSON to CSV and a streaming data pipeline or whatever, you're probably going to end up using a sync at some point. Oh, the first type parameter? This is the error type. So this is an infallible stream. Most streams will have some way to fail, and that will be reflected in that error type. And this is actually a more simplified version. There's the Z prefix in Zio means I want all the polymorphic power that you can give me, basically. So this stream here is just a type alias for Z stream, where the R type parameter is set to any, basically. I don't need the environment. It's the same for managed. So managed, you can use managed with the environment as well. You have to use Z managed for that. The Z prefix always indicates, give me all possible power. I don't care how many type parameters there are, I want it maximally polymorphic. That's what Z does. You get like it on expert mode. And then the simplified versions you see here are just for common cases.
Is this a possible substitute for FS2 stream?
You know, I would say that FS2 and ZioStream don't actually compete a lot because a lot of people use FS2 streams for doing data flow programming, so they want to write their whole program as a stream. And this is more, ZioStream is more intended for like that low-level primitive that you use to process files and socket connections and persistent queues and message buses and things like that, where you're not building your whole program out of it. You're just using it in a fixed area to process something that's stream-like. So, I mean, they overlap somewhat, but I would say FS2 is more, it's targeting a bigger set of use cases. ZioStream is very squarely focused on that sort of, you know, we have some resource, we need to process it in a way that doesn't leak. And then the other thing I talked about, unfortunately we don't have time to get into, is ZioSchedule. And ZioSchedule allows you to build these composable schedules using different operators. And it's extremely powerful. In this final example, let's see, where is it? Right here. The exercise is produce a jittered schedule that first does exponential spacing, starting from 10 milliseconds. And then after the spacing reaches 60 seconds, switches over to fixed spacing of 60 seconds between recurrences, but will only do that for up to 100 times. And by the way, as it's doing all this crazy complicated stuff, it's going to be collecting the errors that are being generated during the retry process so we can log them or something. And it turns out that to express this crazy complex retry strategy using Zio requires fewer lines of code and much simpler than this big English text description. Yeah, and that's a fun one to do, but it would take me 5 minutes to do that, and we're over time. So that's it. I hope you've enjoyed the workshop today and picked up something useful. And what I recommend you do is, if you like this, work some more exercises. Also hang around on the Gitter chat room. So it is located at gitter.im/zio/core. So me and lots of other contributors hang out in there and try to help answer people's questions. And then also, if you're interested in contributing, we can always use more contributors, especially, you know, doing docs or bug fixes, or you don't have to take on a big heavy project. You can go in there and write a one-line sentence to explain something in the microsite, and people will love that. It's be a huge help if you're ever interested in contributing. Thank you very much. I will see you in the keynote room.